Now, that is why so you need to have different distances between the source antenna and the transmit antenna. Now, in the case of your near field, what happens is your near field you don't have this distance criteria. Even if you are having this, if you have an antenna here and you go to 4 lambda or 5 lambda and put a probe here, you can scan on the aperture and you can get amplitude and phase distribution. And this amplitude and phase distribution, you put a Fourier transform and get a far field. You know all that the aperture distribution has some relation with the far field, and that's nothing but a Fourier transform. So once you get so you don't need the advantage of near field is that you don't need a very large infrastructure to go one antenna on this valley, another antenna on another valley, which you put on one building, and then you do the measurement. You in the near field, what we will do is the measurement cannot infinity can be eliminated, and with the less effort, the near field scanning can give much more information than any ordinary far field measurement. And because the signal loss is not there, you know, free space loss is also there in space when any signal is transmitted. So that because of the absence of the free space loss, you get a large dynamic range, and you can even able to locate the fault on the antenna where we are getting amplitude and phase reversals. Amplitude is high, or getting attenuation is there, or your phase variation is very large. You can get that from a sample data. You can easily locate which area of the antenna is having a problem. Unlike in far field, you get only the output. You don't know what is happening inside the antenna. But in the case of near field, you are able to locate the pinpoint area. That it is a very useful tool for diagnosis of fault in the antenna, especially for the phase array. Because if one of the element is not working properly, then you can easily use this near field technique to find out the error in the. Now, the measurement can be carried out without the scheduled disruption. Okay, this is because you don't have any. You can do this measurement within this room. You don't need to go outside. So you are all weather agreed, and sometimes the antenna which you are making cannot withstand the vibration. It is not meant for weather conditions which are required. Like some materials are hygroscopic in nature, so you cannot use that material in the open space. So that will be very essential to do such measurement only in the near field. Then there are RF shielded and controlled conditions and no outdoor reflectors. Because what is happening is today our UHF band, low frequency, because of our mobile communication, even your signal level, even if you put a probe outside, you will get a lot of signal strength in this. And if you are measuring the performance of your antenna, both the signals are getting mixed and you are not getting a proper. So that is why generally these type of antenna measurement ranges are there in a very isolated places. One other place I know is in Bell Ghaziabad. Bell Ghaziabad is having one test range in Sona district, I think somewhere in Haryana, where they are having two towers, and there are two valleys are there actually. Two hills are there, one very big valley is there. And there they are keeping, because they are free from all type of interference are not there. So one can test even 8 meter antenna, 9 meter antenna mounting on the test range. Because outdoor reflections becomes very prominent when you are doing, yesterday as I was mentioning, 30 degree cross pole measurement we have to carry out. That means all the signal level in that area should be less than 30 degree. Then only you can pick up the signal of your antenna, which is 30 degree and better. So the errors in the far field is, we say if it is 2D scale by lambda, what is happening here is that if you are having a outdoor, this is the antenna, suppose, and you are getting a spherical wavefront, and at one particular location, if you see here, you are getting a plane wave. Your amplitude and phase variation is very small. So because of that, so if you see, that is what I have mentioned there. If this distance you take 2D square by lambda, this 2D square by lambda, then if you see the variation in this region, you calculate this angle theta, and then you will find out the variation in the phase delta phi is of the order of pi by 8. So this is very important because the antenna, suppose you are testing here, and this is the antenna which you are testing on this antenna. What is the curvature of the phase which you are getting on the reflector for which you are testing? So the amplitude taper, that is called your the phase and amplitude of the plane wave becomes very important. So the periodic reflections. So that is why we are able to get a phase variation of pi by 8, and that gives that also does not give very accurate measurements. So you have to go sometimes 4d square by lambda or 8d square by lambda. So you may have to go to very large distances, maybe 10 kilometers or 15 kilometers, and it is not possible for to do such measurements in reality very accurately. So what is the solution? Now another error which is there is the periodic variation called reflection, inductor coupling between antennas, radiation coupling between antennas, interference from a spurious radiating. Now what is the alternative then? The alternative, so this is one tower. Earlier in our stack also we used to have this tower, and we used to keep a antenna on the top, and another tower is there on the transmitting side, and we are measuring the performance of the antenna. But today, this is the one which is there kept on a positioner. I saw yesterday in your lab you have one probe which is, he showed me Mr. Dr. Patnaik that you are moving the antenna and then you can record your amplitude and phase, or probably the signal strength, and you can note down the angular information. But what we need, as I showed you first, this thing that antenna radiation pattern is not a single cut; it's a three-dimensional cut. You have to go in theta and phi in all the cuts. You have to take. So that is why you put the whole thing in the positional. Even these trees which are there, they are good, though they are good observers and they give a reflectivity in a arbitrary direction. But sometimes when we are talking about 30 dB and 35 dB, these also generates the noise which is not able to allow you to characterize your antenna properly. So you are seeing even this fixture which is used to mount the antenna can also give you reflections, and that is why the designer team have put some absorbers here so that these signals can be absorbed. So the one solution which came later on in 1980s, that was the compact ranges. Does anybody know about compact range? No. So what happens here is you try to generate in the closed room a very large 2D square by lambda. Suppose I want delta phi of the pi by 8. Instead of going in kilometers, I should be able to generate the same, simulate those in the closed room. Plane wave front, yes. So how to do that? So there are different geometries are used for generating a plane wave where you have a source and you generate a plane wave, and this plane wave we are going to keep our antenna, and then we will characterize our antenna properly. So there were different configurations were there, and they were merit and demerits were. I will not go into that. So this is that what we are having right now in our Ahmedabad, where we keep each antenna is 5.5 meter, and each antenna we are testing. We just see the size of from the two persons are standing there. Here we mount the antenna, and this is the two reflectors geometry where we are able to generate the plane wave of the quality of 2d square by 8d square by lambda. 8d square by lambda, 4 times better than 2d square by lambda, and then we are able to, with all the walls you are seeing are covered with absorbers. So all signals which are getting, nothing is coming and reflected, even though of the order of 45 dB, because each absorber, depending upon the incidence angle, it absorbs the power. So still we are getting nearly 40 to 45 dB down at this level, but that is sufficient for us for today's requirement, where we have 30 dB cross correlation. We have to measure the side lobes. An antenna is kept here and source is kept here. So this is nothing but a Cassigram geometry, where two reflectors are, one is a reflector and the main reflector, and we are able to do the measurement you see even the wall, even the flooring, the floor is also covered with absorbers. So when this different, and each absorber, the design of the chamber is done in such a way that that the absorbers, depending upon the power which is getting reflected from the different sources, the absorbers rating accordingly are being kept there on the particular wall. And the total the chamber is shielded, and the size of the chamber is of the order of 20 meters by 14 meters by 14 meters. And you see even the lights which are there, they also can generate reflections. So the material which is selected is such that they don't interfere, or even if they interfere, they should not come. My antenna is kept here, they should not interfere with the signal which is coming from this wall. So this is a chamber where we do all the antenna performance, and in this chamber we do even the after mounting the antenna. This is a satellite. We mount the antenna on that, and then move the whole satellite and see how it is going to work in our space. So this also we do the testing of antenna integrated with the spacecraft in a compact antenna test facility. So this is facility which is so after this, once we do the characterization, this is how it is mounted in the on the positioner. This is the reflector. This is feed. There are two feeds are kept there. So after we do this measurement, how it works. See, this is the source, this is the sub-reflector, main reflector, and this is your DOT on for which you do want to characterize. The rest of the instrument becomes the same which we use in our outdoor facilities. The only thing what we have done and major changes, the sub-reflector and main reflector are generating plane wave in a. But still, when in a chamber, when we keep the focal point at the focal point, this is my the source of plane wave, and here we can keep our antenna. But still, some of the direct radiation comes from this directly to this. That is the reason we have to put a baffle here, and you must have seen this all having a sharp edges. This is only to so that no diffraction occurs from, because even a circular, if it is a circular in shape, then also you get a very nice RF signal at this point. So to avoid that, you are seeing even the here also you are seeing the sharp edges here. They are called serrations. The serrations helps in reducing the diffractions from the edges of the reflector.
So don't they contribute to the diffraction at such high frequency?
No, they contribute to diffraction, but diffraction, these edges are having a design, they are not triangular, they are cosine phase shaped, so that the diffraction from this tip and this tip, if it occurs, they cancel each other. So at different frequency, and even if it occurs, it may be occurring from a tip now. Okay, now the tip is giving, if any tip is there, it can scatter energy in all the directions. Okay, now the scattering, because it is in all the direction, it is not giving in a coherent way, so the interference signal which is coming in the quiet zone area, this area, it will be very less. So that's the reason they go for serrations. So you have now advantage of this compact ranges, you need not go outdoor, you have to do a automatic measurement with the reduced time and manpower requirement, and one can measure the very low level of cross polarization in side lobes, and controlled environment, because for the spaceborne antennas, because they have to work. This material which we use for spacecraft is a carbon fiber, and the carbon fiber has a hygroscopic property that if the water is poured onto that, the whole material gets spoiled. So that's why the control environment becomes very important, but it can withstand the temperature of minus 180 degree to plus 200 degree in space. But when it talks about this water content, then it spoils the property of the material. So that's why the control environment becomes very important. So we can have a 45 degree reflectivity at the normal incidence for the absorbers. That's why all these are being kept. So this is a general specification. We now have measurement facility of 200 gigahertz in Ahmedabad, where we can measure of maximum size of antenna is 5 meter. We can measure and with the amplitude and phase ripple of the order of 0.5 dB and 6 degree. Now you imagine, even with the 0.5 dB and the phase ripple of 6 degree, we cannot do the measurement better than 0.25 dB accuracy. See, even with the 0.25 dB accuracy, 0.25 to 0.35 dB only accuracy we can do the measurement, even with such a 8 decibel lambda phase errors. And cross polarize, of course, we can do the 40 dB and better. Yeah. So these, there is the one sliding. The whole positioner is being put on a slide because we can do the, suppose when, even when we are talking about 40 dB or 30 dB errors, we are talking about error signal in the space. When we are talking about that, then maybe antenna is being kept on a positioner. There may be some signal, a direct signal, and there may be one 40 dB down signal error may be there. But this also may cause some error into my the side lobe when we are predicting. So when if I change the position of my antenna on the because of this, by moving on the slide, I can there are certain techniques by software one can even improve this error by using called antenna advanced positioning characteristics. That is called antenna pattern correction technique, where simply like you have seen space diversity, where people have changed the phase. Similarly here also we change the location and again do the measurement and take the averaging of this, and we can, there are algorithms available by which we can reduce the number of errors in the. Yeah, I tell you that antenna measurements in particular is such a subject where even I have seen that. I was there in Holland for 2 years. One of the engineers, he worked there for 1.5 years and he got a PhD in antenna measurements. Imagine, his topic was far field measurement in time domain. So it's such a wide, people generally have a feeling that measurement design only is the area where people do the more this research. Even the measurement place is also, there are a lot of research going on, and this is a very deep subject where lot of efforts are required, because even if you do develop a very good antenna system, unless until you have a very better system for your characterization, to no purpose can be served if you don't understand the performance, how to measure it without any error. So this is how the total setup is. Now this is what I was telling for the far field and near field. In a near field, what happens is you start taking from the reflector, you put a probe and start taking the amplitude and phase, and then wherever you have fault, you are seeing the currents are maximum where you have the red maximum in the center, and you are seeing here something is getting formed here, so you can easily locate and see that your algorithm is not working properly in the amplitude and phase here on the antenna. You can go there and pinpoint that area and correct that. So this is a way even people are using holographic techniques for correcting even the mechanical like parabolic dishes or any type of frequency selective surfaces. One can easily work out where is the error, because it's not important whether it is giving the design, it's more important in how to correct that. So this techniques gives you that flexibility. Then you have to, when you talk about test facilities, how to do the measurement performance, you have to put your antenna on a shaker and see whether it can vibrate properly when anything damage occurs or not, because it has to withstand, suppose it can, even to when you are transporting one antenna to another place, it has to go on a road, then there are certain conditions you have to meet for your vibration specifications you have to give. For that also you have to use the shakers and see whether it can withstand those pressures, because it is very easy to design an antenna which is very rugged, but it will be more costly and more heavy. So you have to go for a very design which is having a more less in more performance and less in weight and cost. So these are the various facilities which we are using. One of them is this, and second is this. This is the one which we are using for our multi-layer antenna technology. We are using this facility to calibrate that. Then we talk about, okay, this I have not made, in-orbit antenna testing. When we are doing the antenna, we are, this orbit antenna is in the in orbit. What happens? We have to first clear one by one each system and say that this whole system is working fine before we hand over the satellite to the nation. What we do is we perform the antenna testing. We again take all the cuts by moving the satellite in space. We rotate the satellite in pitch and roll for limited angles, for suppose say 5 degree or 6 degree. We rotate that by using the fuel of the spacecraft, and then we from the ground station we are able to take the pattern measurement, and then once we get all the amplitude and the phase or your co and cross polarization signal, then we say yes, it's working. Otherwise we have to say that this antenna is looking towards India or it is looking towards the sea. So we have to pinpoint where is the bore side, where is the cross polarization. So we have to do in-orbit testing, and for that what we have seen is that this in-orbit performance is very much matching with the whatever we do the performance testing in our compact range. And this is because this 80 square lambda is equivalent to 36,000 kilometers. This quality of the plane wave is similar to that. That's why the errors are more or less same. That's the reason we are able to get a very close match between the in-orbit testing and the predicted measured performance of a antenna. Now I talk about PIM. PIM is the one which is deteriorates the communication or quality of the communication. What happens is if you have a dissimilar material in a waveguide or in any transmission line, there may be a joint may be there, or maybe some cracks are developed or some different it becomes more like a capacitance. Wherever you have a high current density, your capacitance effect comes, and then the capacitance is a non-linear device, and you may start getting some new frequencies get generated into that. It acts like a diode. Okay, then in that case what happens is you start getting different frequencies and which are not a wanted signal. So long it does not affect your performance, you don't bother. But suppose that frequency band whatever gets generated falls into your own communication signal level. Like you transmit the frequency generally from 3.4 to 4.8, and you receive the frequency from the 5.8 to 6.4. Okay, 7 gigahertz, and another Ku band is also there. Suppose because of the transmission high power transmit signal, you get a 3.4 to 4.8 signal is there getting transmitted, and you get a PIM. And because of that intermod product, you get a signals which are generated, harmonics are developed in the Ku band, or it can be even in lower F band also, or C band. So what happens in that case is you start getting the poor quality of communication because your received signals is superimposed by a noise, but this is nothing but a noise. Very common problem. In 1980s and 90s, people started worrying about this, and now they are even asking any international standard. They ask us to measure the performance of your passive intermodal product is getting generated or not, because in any feed in any antenna system we never use one single material. Even the adhesive which we use, adhesives which are there, basically resins, they are having a different quality. So they are dissimilar materials create a PIM, and that has to be measured. And because this is what I was telling you, that this occurs because of the nonlinear VI characteristics. So how do you measure it? Yeah. So how do we measure it? What we do is suppose we have an antenna and this is the feed, and we pump the one signal and with the necessity power, and then we try to get this. We predict what type of harmonics can be there in the system, if at all there any PIM occurs, and then we have to design the tailor-made filters and the receivers in such a way that we get a sufficient dynamic range And we have to calibrate the system up to minus 40 dBm. You see, the minus 140 dBm signal you have to calibrate, and which can measure PIM as low as minus 200 dBc. So you have to measure this because you have to worry about the very minute signal can create a havoc in the spacecraft, or it can create even in the local your ground segment also. Many times we have seen that PIM is a very common phenomena which occurs in a high power system wherever the current densities are large and wherever we are sharing the transmit and receive capability into a single antenna system. So this is how you are seeing the system. Two feeds are there, and then one of the feed is energized, and then another feed we see what type of performance we are getting from the output of the another system. Again, these all measurements are in radiation mode, so all the measurements has to be carried out in an anechoic chamber, which is nothing but having a shielded absorbers are there, and you have to see that no other source of radiation should be there. Even we have seen there are certain papers are available who have done a lot of work on AC ducts, air conditioned ducts also give the PIM generation, because there also your power suppose high power you are using, and though there may be some non-linear contact there also, and those tunneling effect, and they propagate in the tunnels, and inside the chamber you start getting a signal of the different order of the frequency. Okay, so this is how you have to make the different filters. You know your what type of you have to mix two signals. This is one, this is second, and you mix these two and use the diameter, and then you send a signal. And then here you are measuring after a very low noise amplifier input, because you need to measure minus 200 dBc. So for the second feed you measure the output and see whether this frequency band occurs, this PIM occurs or not. So the PIM is a very important consideration wherever we talk about high channel capacity in the communication systems, and generally this type of behaviors are available in ferrite materials and in geometry with the high current densities which show very poor PIM performance, and environmental effects also often deteriorates. Because if suppose the humidity is there inside, or due to the any dust is there inside, even when you wrap these components in a polythene bag, the chemical which is used here in the polythene bag is also can deteriorate the performance of a PIM or your other basic parameters like multifactor. I will not go into detail of that. But so the environmental effect, how do you store the component, that also becomes very important. So the results are difficult to quantify. It cannot be concluded that reading a few basic designs will. So even if you say that I don't have any, my design does not allow any PIM to get generated, but because of the fabrication processes, or but because of the handling, how you are handling, and how you are storing it, and how you are integrating it. Even when you integrate two components, there may be gaps maybe in the flanges. So those all, because of all these reasons, you need to carry out the PIM characterization, the very important parameters in this thing. Now the last is our G by T measurements, where I don't know, I am sure you must be knowing that this is called the noise figure of this is called the figure of merit of any antenna system, and we generally measure the ratio between the gain and the noise temperature. The gain, everybody knows how to measure the gain, how do you measure the radiation properties, but how do you measure the noise temperature? That is the only key in this. How do you measure? Because you know the noise temperature of your device or low noise amplifier. You know the noise temperature due to suppose you have a dissipation loss, but you need to measure them. Even the noise temperature, which is the antenna is getting picked up. The antenna noise temperature, the antenna noise temperature itself, it depends on the noise, your side lobe components, and what type of source it is looking towards. If the antenna is looking towards the sky, then the sky you have many galactic sources. These sources they are basically radiating in microwave signals. Their noise is being picked up by the side lobes of the antenna. And if it is, and the back lobe is there, is picking the ground, you are having, earth also is transmitting is a major source of in the micro region. So this also, back lobe also picks up the noise from the ground. So any antenna which is mounted on the, suppose on the spacecraft is looking towards the ground, so the main source is the ground itself. The ground itself is picking, transmit, when we say nearly 300 Kelvin temperature is there over the ground itself. So you are in the microwave frequency. So you all the time when you take the G by T ratio, you take the G as the gain of your antenna and T will be the your noise picked up of the antenna is nearly 300 Kelvin. So if you convert the 300 Kelvin into dB and then you subtract that from G by T, and that's how you get the G by T ratio. But when we are measuring the G by T of a ground terminal or a ground system which is located, suppose depending upon where you are trying to do, we have to see how to measure the G by T. Then again what we do is we take the antenna and put it to the noise source which we know. Today we know that moon is the one which is the noise source, sun is another one which is a noise source, and all the galactic stars like your Cassiopeia, so their noise flux density is regularly monitored by US one of the agency, and we know it can be predicted very accurately, and any changes which are occurring there in the space are getting monitored at one, and we can get this noise source information from them. And if we know the noise source, then how to measure the antenna noise temperature? By comparing the antenna power by first to the clear sky, and we will get the no noise. The noise picked up will be from the clear sky condition will be zero. We are assuming that. And when we take it to the particular noise source, hot and cold, we put your antenna to the hot and cold source, and then we are able to compare this, and we are able to see what type of noise the temperature is of the antenna. And when we take a ratio of these, then we get the G by T. So convenient way is that we obtain the G, one could determine G and T separately. That is one way, but they are more difficult to measure. So generally people do G by T measurement directly into the space with the instruments. And this is how one of the methods is that I told you that you take the antenna to the sky free region of strong sources, and then once you have background galactic sources, and then there will be a noise picked up by the side lobes, and then you will take the receiving system is related to the system noise temperature, you get the T, and then you convert this T into Fn. And then one can easily measure the sun and cold sky condition, see the measurement of the Y factor, and can find out the G by T by using this expression. So the idea is just to tell you that antenna also is generally, this is what I was telling, that at many places, the United States of America, they are having space command which is running at different places, and they are measuring the solar flux density, and even for some stars regularly monitoring, and so which help give us the number of noise, how much power flux density is there in which area, and that number is very useful for calculating the G by T. So the idea was that to give you a glimpse of, we always know the noise temperature of a device, noise temperature of a low noise amplifier. The noise temperature of an antenna is also very important, because that gives a figure of merit for you. So this is one calculation we carried out for one of our antenna which is working at 1.4 gigahertz, and we calculated the G by T. And another indirect method is that we can compare the two antennas together. One antenna we already know it has been calibrated, and then we can compare this antenna with the calibrated antenna, how the performance of the G by T is. One can compare the G by T, and then we can calculate, but there is some error there. See here, we expected value of G by D was 9.4 dB, but what we measured with the comparison method was 7.4 dB. So this is more inaccurate method, but certainly one can use this as a for. So this is one which I was telling you by comparing comparison method, and one can use simply your free range radaring equation to calculate the free space loss.